All right, welcome back. 9.3 AP Environmental Science, the greenhouse effect. You've been waiting for it all year. So here's a fun little comment for you guys to enjoy. I'll let you read over it for a moment. Yeah, so this is probably me someday when I retire, when I get close to retirement. There you go. Yeah, Venus's ozone or Venus's greenhouse effect. Runaway. Have fun. So, what is the greenhouse effect? Well, let's start at the beginning. Incoming solar radiation, also we would refer to it as UV and visible light, those come into the Earth from the sun. Thank you to the sun. A third of that is actually reflected back into space. UV blocking from the ozone and just in general the clouds that we have, the stuff in the stuff in our atmosphere. A third of it is reflected back into space, also due to the albedo effect. The remaining, the remaining light can be absorbed by clouds, the planet's surface, and then that is what becomes warmer and then emits infrared radiation. So that radiation can then be absorbed by GHGs, greenhouse gases, or emitted back into space. So you can imagine incoming solar radiation comes down, warms the surface. That warming then radiates back up and can either be absorbed by greenhouse gases or emitted back into space. Without greenhouse gases, it would still be very, very cold here. So more greenhouse gases means more infrared is going to be absorbed and emitted back to Earth. So that is where, we have a fine balance. We need enough to keep enough warmth here, but we don't want so much that it makes it too warm. So this is just a broken little easy diagram that I will probably give to you guys to fill out, and we'll fill it out as a class. So don't worry about it for right now. So the process should be in equilibrium, short term, okay? In equilibrium. The short term, the inputs could be higher, lower, and that's what causes global warming or cooling. That's what creates these ice ages. So if we look back from today, 100,000, 200,000, all the way back, we can see these periods where average global temperatures have risen and fallen and 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 risen and fallen. Okay, so that makes sense, right? We're currently in an interglacial period. So glacials are the lower area, the interglacials are the upper areas. Down here, these would be considered ice ages, okay? Now, nitrogen and oxygen is 99% of the atmosphere, and nitrogen and oxygen are not greenhouse gases. That's important for us to know. What are the greenhouse gases? Well, there's water vapor. This absorbs more infrared than anything else, but it does not persist. It has a cycle. Carbon dioxide, methane, nitrous oxide, and ozone. These are our 5 deadly greenhouse gases. And then CFCs, which are not natural. We throw them in there, but there's a little star there because they are not a natural thing. Everything else, carbon dioxide, methane, ozone, and nitrous oxide, those are all things that naturally occur. CFCs are something that are man-made that we then release into the atmosphere. Go humans. All right. So an easy way to remember these 5 greenhouse gases, we call our mothers now. We call our mothers now. Water, carbon dioxide, ozone, methane, and nitrous oxide. Those are the 5 greenhouse gases. Without these greenhouse gases, the average temperature on Earth would be 0 degrees Fahrenheit. We kind of need them, okay? Our actual average is 57 degrees Fahrenheit. So we're going to fill out this table, and then we're going to end the video. So I would recommend that you draw this table. That way you have some information, because we're going to talk about concentration of each of these greenhouse gases. We're also including CFCs. The potential over 100 years, and this is how we can compare different greenhouse gases to each other to determine which ones are worse for the atmosphere. And then the duration in the atmosphere. How long do they persist in the atmosphere? Because like we said before, water vapor is pretty bad, but you'll see in a moment, it does not persist. So I'm going to go through each of these fairly quickly or slowly, depending on how I decide, but you can pause at any point to record the information. I really, really recommend that you get this stuff down. So, the concentration of water vapor really depends on the temperature, right? The temperature is what determines how much water vapor is able to be in the atmosphere. The potential, the warming potential over 100 years of water vapor. Oh, I guess we're just going down the concentration. I forgot that I put it in that order. Whoops, okay. Concentration of CO2 right now is 417 parts per million, and we'll dive into deep information about that number. Methane is 1.8 part per million. Nitrous oxides are 0.3 parts per million, and chlorofluorocarbons are 0.9. Okay, so you can see carbon dioxide is definitely the higher one in here. Water vapor depends on the temperature, but everything else is fairly low relatively to each other. Now we'll look at the warming potential. The warming potential, again, this tells us how much potential it has to warm the surface. So when we think of water vapor, it has a warming potential of less than 1. When we think of CO2, it has a warming potential of 1. CH4 is 25. Nitrogen oxide is 300, and CFCs can be anywhere from 1,600 to 13,000. And these are just relative to each other. That's the most important thing, so we can see their global warming potential to each other, okay? So methane, 25 times more, has 25 times more potential of warming the earth than carbon dioxide, and so on and so forth. This is where these things come into importance, because how long do they persist? Well, water vapor typically will stay in the atmosphere for about 9 days. The water cycle pretty much maintains that problem, right? Carbon dioxide can go for years. It really, really depends on the ability for the ocean to absorb carbon dioxide. It depends on carbon sinks, the plants that can absorb the carbon dioxide. Those are really, really important parts of the carbon cycle that really change what can happen. Methane will stay in the atmosphere for about 12 years. Nitrous oxide, 114 years. So you can see the ones that are worse for the atmosphere, part of that has to do with this right here. This is why these numbers are so much different, because they stay in the atmosphere for longer or shorter periods of time. So you can only imagine how long CFCs might stay in the atmosphere. Anywhere between 55 and 500 years in our atmosphere once released into the atmosphere. And that is why this is a big part of when we look back at ozone depletion, this is why, even though the Montreal Protocol has not significantly reduced the amount of CFCs in the atmosphere from the period it was, it's because those CFCs are going to stay there for a long time. All right, so that's going to be the end of this video. The next video, we will continue talking about the greenhouse effect, but I did promise that I'd try to keep these videos under 10 minutes, and I'm doing my best.